Hello guys, welcome to my YouTube channel Campus Explained. In the previous video we have dealt with clocks. Now in today's video we will deal about SR flip-flops. We will deal that how to implement, how to design the SR flip-flop using NAND implementation, and then we will see about NOR implementation. Talking about the logic signal, it takes two input S and R, that stands for set and reset, and it gives output as Q and Q bar, and it takes one more input that is called clock. The clock is something that makes it different from the latches. The clock controls the input of the SR flip-flop. As its name is SR or RS, the meaning is set. If the flip-flop store one value, it is said to be the set, and if the flip-flop stores 0 value, it is said to be the reset. We will talk about this in the comment section state. In the logic circuit, there are 4 NAND gates that are used here. So the dotted line represents the SR latch. If we add the 2 NAND gates in front of this SR latch, we will get the flip-flop. The difference between latches and flip-flop is that we use the clock signal to control the input of the flip-flop. So for connecting the clock signal to the flip-flops, we need to use 2 extra NAND gates to the latches, and its whole make SR flip-flop. Now as we are using the NAND gates, first of all we need to know the truth table for NAND gate. First thing is that we are taking 2 values as the input, A and B. So for the possible combinations are 2 to the power n, 2 to the power n, if 2 is equal to 4. So 0 0 0 1 1 0 1 1. So these are the 4 possible combinations that are used for making the truth table of NAND gate or for the functioning of NAND gate. So for 0 and 0, if we multiply 0 and 0, we will get 0, but its complement is 1. Same, if we multiply 0 and 1, we will get 0, but its complement is 1. Then 1 and 0 we will multiply, we get 0, but its complement is 1. 1 1 we multiply, we get 1, but its complement is 0. We can see or observe a pattern here that if any of the input is 0, we will get 1 as our output. This concept we use to make the characteristic table, then excitation table along with the truth table. So this will be our sequence. So in the first case, we will take clock 1, S value as 1, R value as 1. Now we have clock signal as 1, this value is also 1, so it will become 1, and S value is 1, R value is 0. So talking about the first NAND gate, if 1 and 1 is here, we will get 0 as our output. Now about this NAND gate, second NAND gate, we will get 1 and 0. If we multiply it and take its complement, we will get 1. Now this 0 will come here, this 1 will come here. As we have talked about that observation that if any of the input of the NAND gate is 0, we will get 1 as our output. So in the third NAND gate, we are getting 0 as our input. So we will get 1 as our output, and this output will be given to this NAND gate, and this 1 and 1 will become 0. And this 0 will go to the input of third NAND gate. So 0 0 1 1 1 0. So if we talk about the Q, we will get 1. If we talk about the Q bar, we are getting 0. And we know that whenever the flip-flop store 1 value, it is called to be the set. When S value is 1 and then Q value is 1, this case is called to be the set for SR flip-flop NAND implementation. Talking about the second case, take the clock value as 1, S value as 0, and R value as also 0. So this will become 1 and this also will become 1. Now S value is 0 and R value is also 0. As we know that if any of the input of the NAND gate is 0, then we will get 1 as our output. So output will be 1. Here also this output will be the 1. Now 1 will be coming here, here also 1 will be coming here. As we do not know that what will be our output value, as we are getting 1 1 here, so we don't have such type of observation. So for this case we use the previous output. So previous output here is 1, here previous output is 0, so we will take this output. So 1 and 0 will give 1 as our output. Here also 1 and 1 will give 0 as our output. So if we are giving 0 0, it is coming 1 0. So simple. So as the previous state and the next input is same, so we write it as no change. It means there is no change between the previous output and this output. Talking about the next case, we will take clock value as 1, clock value as 1, S value as 0 and R value as 1. So clock is 1, so 1 will be given here, here also 1 will be given. Our S value is 0, so we will write S value as 0, we will write R value as 1. Now this 0 and 1 will make what? 0 and 1 in the NAND gate, it will make 1. Here 1 and 1 will make 0. It means the 1 will be coming here and 1 will be coming here and this 0 will be coming here. So we know that if any input of the NAND gate is 0, we will get 1 as our output. So this 1 will be coming here and 1 will become 1 and 1 will be given 0. So we are getting 0 and 1 as our output. So 0 and 1. Now here the output value is stored as 0, and whenever the output value is stored as 0, when S value is 0, we call it this case as reset in SR flip-flop NAND implementation. At last we will take the clock as 1 and S value is as 1 and this value also as 1, S and R value as 1. This is our last case we will deal. Now we will make clock value as 1, it is already there, R S value as 1, R value as 1. Now when both value of the input of the NAND gate is 1, we get 0 as our output. If both value of the NAND gate is 1, we will get 0 as our output. Here also 0 as our output. This 0 will be going here and one more 0 will be going here. 1 and 1 will become 0 and this 0 will be carried out here. Now if any of the input is of the NAND gate is 0, we will get 1 as our output. Here also 1 as our output. Without putting mine in this, directly write 1 as our output. Now we will write 1 and 1. This state here, this state is called invalid state. Now the question arises that why do we call this state as invalid state? Here we can see that the output should be complemented to each other, but in this case the output are not complemented to each other. That's why this state is called invalid state. It means that it should be 0, either this should be 0 or 1, or either this should be 1 and 0. This thing we call as don't care. Don't care means any value can be there, either 0 or either 1. So we will represent this one as don't care. We have completed the truth table. Now we will make the characteristic table for SR flip-flop. For the clock reason, this is always 1. Clock is always 1. In this characteristic table, we will talk about clock QT. QT represents the previous output and then the inputs and the next output, next or present output, QT plus 1. We also call it as previous state or the present state. Here we have 3 inputs. So how many possible combinations are there? So 2 to the power n, 2 to the power 3 is equal to 8. We should have 8 possible combinations. So these are the possible combinations that we have. These possible combinations are written by, like in binary we will write 1 as 0 0 0, in binary we will write 2 as 0 0 1, 3 as 0 1 0, same wise we can write 8 as 1 1 1. Now there was too much mess in that previous page, so we will talk about the present state in this page. So here Now there is a very nice technique to find the present state, so listen it very carefully. Now you see here we have 3 inputs and we have 1 output. Now we will match S and R values to this truth table to get the present value. Here you see that we have S and R value as 0 and 0. Now in this truth table, where can we find 0 and 0 as S and R value? Here we can find S and R value 0 0 is here in this truth table. Now this truth table says that if we take 0 and 0 as our S and R value when taking clock as 1, we will get no change. No change means it will be same as the previous output. Here our previous output is 0, so we will write previous output, no change. Okay, now we will match this 0 and 1 value in this truth table. Where we can find 0 and 1 as S and R value? Here we can find 0. This is called reset. Always remember that whenever the reset will be given, we will write 0 as it is. This is, you can say, as a trick, or set value we will write as 1. So in 0 and 1 we are getting reset. Reset we can write it directly 0. When 1 and 0 is there, 1 and 0 set means 1. Similarly, when we are getting 1 and 1, here this is don't care, so this is invalid state, we will directly write it as invalid state or don't care. Now again 0 and 0, 0 and 0 we can find it here, no change. No change means it will be same as the previous output. Here the previous output as 1, we will directly write it as 1. We will write similarly 0 and 1. For 0 and 1 we are getting the reset. Reset means 0. For 1 and 0, we are getting set means 1. Again for 1 and 1 we are getting don't care. That's it. This is too easy. Now from this characteristic table we will form the excitation table. Now we will make the Carnot's map. For Carnot's map we have 3 input combinations, QT, S and R. So we will make 3 variable K map. So for 3 variable K map we should have 2 to the power 3, that is 8 boxes, 1 2 3 4 5 6 7 8. Now we will see that in QT plus 1 where we are getting 1 as our output. In this case we are getting 1 as our output. So for this case we are getting 1. So 0 1 0, 0 1 0 we are getting 1. For this case 1 0 0, 1 0 0 we are getting 1, so it is marked as 1. Here we are getting 1 1 0 as 1, so 1 1 0 we are getting 1. For don't cares we are getting, for this case we are getting don't cares, that is 0 1 1, so 0 1 1 and 1 1 1 1 1 1 we are getting don't care. For other cases we are getting 0. So here we can map it as quadr here, then we can map it as pair, this one we know the K maps very well, so we can map it like this. We will write each and every combination of boxes that are making this. So we have 3 input QT, S and R. For this box, let us consider for this box, see it very carefully. For this book, what is the serial number for this? So 0 1 1 0 1 1. For this box 0 1 0 0 1 0. For this box 1 1 1 1 1 1. For this box 1 1 0 1 1 0. Now we have only to take that case where only 1 is present or either only zeros are present. We have to ignore that case that contains the combination of zeros and ones. So let us take this case. It contains the combination of both zeros and ones, so we will ignore this case. Here we can also see that it contains the combination of both zeros and ones, so we need to ignore this case. Only this case set has to be counted, so we are getting S. Now for this pair, now what is the serial number for this box? 100 100. For this box 110 110. Now same thing, if we apply that, if the box contain the column contains the combination of zeros and ones, we need to ignore that case. If the box contain only the ones, we need to tick that case. So here we can get QT. Here the box contain only zeros, so we are getting R bar. You know, 0 means bar or complement, or 1 means the same thing. Okay, so for this we are getting the characteristic expression as QT into R bar plus S. Once we completed the characteristic equation for this SR flip-flop, we need to find the excitation table. For this, we always need a characteristic table. In this case we have two number of inputs, so 2 ki power n, that is 2 ki power 2 is equal to 4. So we have 4 possible combinations, that are 0 0 0 0 1 1 0 and 1 1. Now for making the characteristic excitation table, listen it very carefully. So for qt and qt plus 1, we need to find where this qt and qt plus 1 are there in the characteristic table. So here the qt and qt plus 1 both value are 0. For this value we can find this 0 0 here, again we can find this 0 0 as here, means we have to find 0 0 in this characteristic table in the column qt and qt plus 1. So in two rows we are getting 0 0, this row and this row. For this the s value is not changing, that is constant here, 0 and 0, so we will write 0. The r value changing from 0 to 1, we will only consider these rows only, it is changing from 0 to 1, it means this is don't care. Now we will see the case 0 and 1 in this whole characteristic table. We will check the case 0 and 1, where we are getting 0 and 1. Here first we are getting 0 1, now we will again check where we are getting 0 1. So only for this case we are getting the 0 and 1, so we will directly write the s and r values. So this is 1 and 0. Now we will check for 1 and 0, where we can find 1 and 0 in this characteristic table as q and qt plus 1 column. So 1 and 0, where we are getting 1 0, this case 1 0 1 0 1 0 1 0. Okay, for this case we are getting 0 and 1. Now we will consider the 1 and 1, where we can find the 1 and 1 here. 1 and 1, first this one 1 and 1 1 1, this case, again this case 1 and 1 as qt and qt plus 1 column, qt and qt plus 1, that's it. So we consider the s value as don't care, because its value is changing from 0 to 1, so s value will be 0 to 1. Again this 1 value is not changing, so we will write it as 1. The next video we will see how to draw a flip-flop, SR flip-flop, using the NOR implementation. That will be way easier if you understood this video. Okay, so if you have any doubt, just tell me in the comment section, we will discuss about that in the comment section. And that's it for the video. Thank you for watching this video. Now subscribe to our channel Campus Explained.